Today we're going to look at a really nice problem I found in the Math Magazine. So our goal is to find all prime numbers a, b, c, and d such that 10 to the a plus b squared is equal to c to the 10 plus d squared. And throughout, we're going to use the fact that only certain numbers are perfect squares mod n. So for example, if we reduce everything mod 4, the only types of perfect squares are 0 and 1. So we can just quickly observe that 2 times 2 is 4, which is 0 mod 4. And for example, 3 times 3 is 9, which is 1 mod 4. And furthermore, all even squares are 0 mod 4, whereas all odd perfect squares are 1 mod 4. Now, also, we could reduce mod 5, and we'll see that the only perfect squares are 0, which is 0 squared, 1, which is 1 squared, and 4, which is 2 squared. Observe that 3 times 3 is 9, which is another 4. And then 4 times 4 is 16, but 16 mod 5 is 1. Now, furthermore, we can check that all perfect squares mod 7 are 1, 0, 2, and 4. And if we're working mod 8, the perfect squares are 0, 1, and 4. Okay, so let's get into our solution. We're going to start by trying to determine the value of d. So I'm going to start with the following claim. And that claim is that d is not even. In other words, d is not equal to the number 2. Observe that the only even perfect, or the only even prime number is 2. So if we're saying that d is not even, it's the same thing in terms of primes as saying that d is not equal to 2. And we'll prove this by way of contradiction. So let's suppose that d is equal to 2, and we'll come up with some sort of problem here. So very, quickly we can plug 2 into our original equation, and we'll see that that's going to reduce to c to the 10. I'm going to move some things around at the same time. C to the 10 minus b squared is equal to 10 to the a minus 4. But now let's observe that the right-hand side of this equation is even, because 10 to the a is always even. Well, unless a was 0, but recall that a is a prime, which means it's bigger than or equal to 2. So in fact, 10 to the a is at least 100. But anyway, all we need here is that this is even. But that's going to break this into two cases. We either have c and b are both even, or they are both odd. Notice if one is even and one is odd, then the difference like this will be odd, but the right-hand side is even, so we know that the left-hand side is also even. So let's break this down into those two cases. So case number 1 will be that b and c are both even, but that means that b equals c equals 2. But if b and c are both 2, and well, d is also 2, we can plug that into, well, either this equation or our original equation, and that'll pretty quickly bring us to an equation that we could solve for 10. So when all is said and done, we get 10 to the a is equal to 2 to the 10, which is the same thing as 1,024. But kind of obviously, 1,024 is not a power of 10. So that brings us a contradiction. So, well, that means that b and c are both not equal to 2. But that means that b and c are both odd. So that's going to bring us to our case 2. So let's see, b and c are odd. Now, well, obviously, since we're working towards a contradiction of the fact that d is equal to 2, well, we should get some sort of contradiction out of this assumption as well. So let's see how that goes. So if b and c are odd, then when we square them, or really take any even exponent of them, we'll get something that's 1 mod 8. Because notice that 1 is the only odd perfect square mod 8. So maybe let's write that down. So that means that b squared is congruent to 1 modulo 8. And also c to the 10 is congruent to 1 modulo 8. Now you could think about c to the 10 as c to the 5, which is odd, and then square that. So that's a square of an odd number, which is 1 mod 8. But next up, what we'd like to do is plug all of this into, perhaps this equation right here and reduce it mod 8. So let's do that. So here we'll, like I said, reduce this mod 8 and we'll get 10 to the a minus 4 is congruent to 0 mod 8 because we have 1 minus 1. In other words, we have 10 to the a is congruent to 4 modulo 8. But observe that 10 to the a is the same thing as 2 to the a because 2 is congruent to 10 mod 8. So here we have 2 to the a is congruent to 4 modulo 8. But now notice that that immediately tells us that a is equal to 2. Because obviously 2 squared is equal to 4, and thus it is 4 mod 8. But if a is bigger than 2, then 2 to the a will be 0 mod 8. So, well, like I said, that means that a must be equal to 2. Okay, but now we can use this along with kind of our original assumption up here that d is equal to 2 to plug it up into this equation, and we get some new equation for c to the 10 minus b squared. In fact, we get c to the 10 minus b squared is equal to 10 to the 2 minus 4. In other words, it's equal to 96. But now if c to the 10 minus b squared is equal to 96, we can factor that as c to the 5 minus b times c to the 5 plus b is equal to 96. But that immediately gives us a nice inequality. Observe that that's going to imply that c to the 5 is less than or equal to 96. But now let's observe that if c is equal to 3, well, 3 to the 5 is bigger than 96. Notice that 3 to the 4 is 81. You multiply that by 3, you get 243. That's too big. So the only prime that c can be is thus 2, because that's the only prime that when you take the 5th power, you get something less than or equal to 96. Okay, so like I said, that means that c is equal to 2. Oh, but notice up here we said that b and c were both odd, but 2 is not an odd number, so that brings us to a contradiction. But that means that we've proven this claim up here that d is not equal to 2, because assuming that it was equal to 2 got us to a contradiction kind of regardless of which path we took. Okay, so now let's move on from here. So we just finished proving that d is not equal to 2. So in other words, d is odd. So let's write that down. So we need the fact, or we'll use the fact at this point, that d is odd. But now let's recall that if we square an odd number, we get something that's 1 mod 4, as we discussed before. So that means that d squared is congruent to 1 modulo 4. Okay, so let's maybe plug or reduce the original equation mod 4 and see what happens. So we'll have b squared plus 10a is congruent to c to the 10 plus 1. But observe that 10 to the a is congruent to 0 mod 4 because a is bigger than or equal to 2. So any power of 10 that's bigger than or equal to 2 will obviously be a multiple of 2. Okay, so that brings us to the following congruence pretty quickly, that b squared is congruent to c to the 10 plus 1 modulo 4. Okay, great. But now where can we go from here? And now that's going to bring us to two cases regarding C. So our first case is what happens if C is odd. Well, if C is odd, then C to the 10 is congruent to 1 mod 4 again, because C to the 10 is a perfect square. It's C to the 5 squared, like we said before. But that means that B squared is congruent to 1 plus 1, in other words, 2 modulo 4. But as we discussed before, 2 is not a perfect square mod 4. So there, we get a contradiction. But, well, what does that mean? Well, if it's impossible for C to be equal to an odd number, then that means that the only possibility is that C is even. In other words, C is equal to 2. Now, okay, so that's good. Now, where can we go from there? Well, let's go ahead and plug that into our original congruence and see what happens. Okay, so if we've got C is equal to 2, then we'll have 10 to the A plus B squared is equal to 2 to the 10. So we might as well write that down as 1,024 plus B squared. And now I'd like to observe that this number right here is even, 10 to the A, and this number right here, 1,024, is even. Whereas we know that this number right here, D squared, is odd. So the fact that we've got even plus something equals even plus odd, that means that what's left over here is odd. So in other words, we have B is an odd number. And now let's work towards the final couple of steps. So let's see what we have here. We're eventually going to have B squared minus D squared is equal to 1,024 minus 10 to the A. And at this point, we're going to work through some cases. So maybe I used orange case 1 and case 2 there, so I'll use green case 1, case 2, case 3 here. So let's look at the possibility for A to be equal to 2. So if A is equal to 2, then we have B squared minus D squared is 1,024 minus 100. In other words, it's equal to 924. So we could write B squared minus D squared is equal to 924. But now let's reduce that mod 8. So if we reduce that thing mod 8, we'll have B squared minus D squared. Oh, but B and D are both odd, which means B squared is 1 mod 8 and D squared is also 1 mod 8. But then if we take their difference, we get 0 mod 8. So we have 0 is congruent to, well, if we reduce 924, we'll see that we get 4 mod 8. But now we've got 0 mod 8 is congruent to 4 mod 8. That's clearly not true. So that's our contradiction there. Now let's move on to our second case. And that second case will be the case if A is equal to 3. Okay, so if A is equal to 3, plugging into a similar equation like this that we have right here, we'll have B squared minus D squared is equal to, well, it's going to be 1,024 minus 1,000. In other words, 24. But now we can just play with small values of prime numbers and, well, see that we can guess and check a solution pretty quickly. And what we'll find is that B equals 7 and D equals 5 works, if you will. And, well, that gives us a solution. And let's circle all of the parts. So we know that C is equal to 2. We know that A is equal to 3. We know that B is 7 and D is 5. So perhaps we could fit that in over here. So we have a solution A equals 3, B is equal to, let's see, 7, C was equal to 2, and D was equal to 5. Okay, so there's one solution. Now let's see if we can get some more solutions. And in fact, what we'll see is that there are no other solutions, and we can take that, or we can take care of that all at the end by looking at the setup if a is bigger than or equal to 5. So if a is a prime that's bigger than 3, it's got to be bigger than or equal to 5. But let's go ahead and take care of that on a fresh board. Okay, so let's just recall that we've worked through all of the cases except for the case when a is bigger than or equal to 5, b is odd, c is 2, and d is odd. So let's see where we can go from there. So I'll take my original equation over here and rearrange it a little bit to get the new equation, which is d squared is equal to b squared plus 10 times a, or 10 to the a, minus 2 to the 10. Okay, great. But now let's observe that if a is bigger than or equal to 5, well, we know that 10 to the 5 minus 2 to the 10 will be bigger than 10,000. So this whole thing is bigger than 10 to the 4. Okay, but if that whole thing is bigger than 10 to the 4, we've got a certain size for d. In fact, this means that d is bigger than 100. Okay, so now we'll reduce this whole thing mod 5 and see what happens. So reducing this whole thing mod 5, we'll see that we get d squared is congruent to b squared plus 1 mod 5. And well, why is that? We'll observe that 10 to the a is 0 mod 5, and then 2 to the 10 is 4 mod 5. And well, that's kind of obvious because it's 1,024. That's 4 more than 1,020, which is a multiple of 5. But we're subtracting that. So we really have b squared minus 4, but negative 4 is the same thing as positive 1 mod 5. But now let's also observe that we know d is an odd number. So I guess d could be equal to 5. When we square it, we get 0 mod 5. But we know that d is bigger than 100, which means nominally it's bigger than the number 5. So that means d squared is 1 mod 5. So if we've got a 1 mod 5 here and a 1 here, well then moving some things around, we'll see that b squared is congruent to 0 mod 5. But the only prime that's congruent to 0 mod 5 when you square it is 5. So that means we have b is equal to 5. But now we can plug that maybe back into this equation right here and see what falls out of that. So that's going to give us the following. We'll have d squared is equal to 10 to the a. And then, well, what do we have here? 25 minus 2 to the 10. So that's going to be negative 999. Now, from here, what we're going to do is finish this off with 2 cases. And this is like a little subtle. It has to do with the types of primes that you get mod 7. So now we're going to work mod 7. All prime numbers bigger than or equal to 5 are of the form 6k plus 1 or 6k plus 5. So our first case will be a is equal to 6k plus 1. So now plugging that right here, we have d squared is equal to 10 to the 6 raised to the k power times 10 minus 999. But now if we reduce this mod 7 by Fermat's theorem, we know that 10 to the 6 is 1. So reducing mod 7, we get 10 minus 999 mod 7. In other words, we get 5 mod 7. So this whole thing is congruent to 5 mod 7. But now we have d squared is congruent to 5 mod 7. But if we look over here at the perfect squares mod 7, we see that we do not get 5. So that's a contradiction here, which means it's impossible for a to be of the form 6k plus 1, bringing us to the last case of this entire problem, which is a is of the form 6k plus 5, which means that we have d squared is equal to 10 to the 6 to the k times 10 to the 5 minus 999. But now reducing that mod 7, again using Fermat's theorem, we see that we get something which is congruent to 0 modulo 7. But now if d squared is congruent to 0 mod 7, that means that d must be equal to 7. But notice now we've got d is equal to 7, and up here we showed that d was bigger than 100. 100 is obviously bigger than 7, so that's our final contradiction. Which means in this remaining case, we were not able to produce any solutions. In fact, we proved that there were no solutions, meaning that this solution up here was the only one. And that's a good place to stop.